So if we start our discussion of chemical kinetics by reminding us that we started the semester talking about kinetics. We, at the time, saw graphs like these, where concentration is on the y-axis and time is on the x-axis. My laser pointer is not showing up. We see that triangle plot decreases over time. That tells us the triangle thing is a reactant. B is a reactant. We see that the square also decreases over time. That means A is a reactant. And we see that the circle increases over time. That means C is a product. So if we remind ourselves of what we did back in the day when we started learning these, we would look at initial concentration. I can't spell. Initial concentration of A is 1.25. Initial concentration of B is 6. Initial concentration of C is 0. We would say we lose some, but we don't know how much yet. But the final / equilibrium concentration of B, that means where it's flatlined over here. We're going to say that's 3. C has flatlined at 2, and A flatlined at, that looks like a 0.25. So we lost 1, we lost 3, we gained 2. So that means we can put those coefficients in front of our reaction to end up with a balanced reaction overall. One more thing to remind you of about these plots before we move along. The moving portion, that's the kinetic region, the changing concentration portion. The flat portion, that's the equilibrium region. Do you remember saying that? I hope so. We have spent the last 7 weeks talking about this region. We're going to spend the next couple of weeks talking about this region. Yeah? Yes. Okay. So why do we use concentration to monitor the rate instead of moles? Well, if you remember, when we started doing limiting reactant this, limiting reactant that, we compared moles of everything because moles are what react together. However, in rate law stuff, we compare concentration because if you have a reaction at a certain concentration and you change the size of the container, it changes the rate of the reaction because molecules must collide before they can react. That's an important thing. If you change the size of the container and have the same number of molecules in it, they're going to collide a lot less frequently in this shape container or in this size container because they're much more dilute. They're not going to collide with each other as much. So the rate slows down. If they're stuffed into a tiny little sack, they collide much more frequently. You have to collide in order to react. Moles are the same in each case, but concentration is not the same. So we keep track of concentration over time because the concentration affects the rate. Did we say all this thing? Yep. Okay. Here's a reaction that's very similar to what we're going to do in our next lab experiment. We have a colored compound. Br2 is a red/red-brown, orange-brown liquid. Br2 is red-ish. When it reacts with formic acid, that's this guy. We don't have to know how that reacts, why that reacts, but when Br2 reacts with formic acid, it creates this, and this. None of these are colored compounds, so I'm going to say these are colorless compounds. And because we create colorless compounds, we can monitor the change in color over time, which we can relate to change in concentration over time. So Br2, there's a lot of it in this dark reddish, brownish sample. There's less, there's none, right? Our eyes can detect those colors, but we can also do an experiment, a UV absorption experiment, to find that 293 is the wavelength of light that is absorbed by this dark sample. We have our little beaker, we pass a 293 nanometer light through it and detect how much is absorbed. This this dark colored sample will absorb a lot of light. This light colored sample will absorb none at 293. 393, dang it. Concentration of Br2 is proportional to the absorbance. Okay, if we plot absorbance over time, it starts out high, it goes lower over time, it goes lower. This is not different samples. This is after a few seconds, here's what it looks like, or a few minutes, or a few hours. After a few more minutes, seconds, hours, whatever, it looks like this. So over time, the absorbance decreases, and eventually it will flatline, and that absorbance thing can be used to determine the rate of our reaction. Right? Right. Okay. Something that we saw before that we didn't use a lot previously, but we're going to use a lot more often now. The rate law. The rate law is something that's used to find the rate of the reaction. Here's a reaction. We've seen this before, actually, this exact one. And the rate law for this reaction is written as rate equals K, and it's popping out of order. Oh, there we go. Rate equals K times the concentration of reactants. Reactants are the only thing determining the rate of the reaction. The products have no effect on the rate of the reaction. The concentration of the reactants are the only thing involved in the rate law. This little k, that's important. Big K means equilibrium constant. Little k means rate constant. Rate equals the rate constant times the concentration of reactants raised to some number. That number up top is usually a whole number. Sometimes that whole number is the coefficient of the reaction, but not always. There's more to be said. Hold on. This specific reaction, the rate law is N2O5 to the first power. So we would say that this is a first order reaction. Coefficient is 1, it's first order. I can plug in any sort of concentration into my rate law, any sort of reactant concentration into my rate law, and determine the rate of the reaction when the concentration equals this. Because the rate of the reaction changes over time, as the concentration gets smaller, the rate gets smaller. As the concentration gets bigger, the rate gets bigger, right? Right. So if I plug in that value, one thing I can do is look for 0.44 on the y-axis, and that's that little pink dot. The rate of the reaction is actually measuring the slope of the line at that instant. Is the slope of the line at that instant different from the slope of the line at this instant? Yes. The slope up here is much more steep. Let me draw a little line. Maybe you can follow me. The slope up here is much more steep. Oh, not that steep. The slope of the line here is much more steep. The slope of the line here much more flat. And over here, even more flat. The rate changes over time. So plug in that math, and I get, plug in that math, I get 2.7 times 10 to the negative fourth. Much bigger rate in the beginning than over here at 0.44, which is even bigger than something over here at 0.2 when you get there eventually. Okay, this really is all about the rate law today. That's what we're going to work on first. The rate law expresses the relationship of the reaction to the rate constant and the concentration of reactants raised to some powers. What? Given a generic reaction, A and B are reactants, so A and B concentration will show up in the rate law. So rate laws have the general formula of rate equals K, that's rate constant, times reactants raised to some powers, times reactants raised to some powers. If you have more reactants, times reactants raised to some powers. If you have even more reactants raised to some powers, you're multiplying all the reactants together raised to some powers. This is A and B coefficient, and note we put a 2 and a 1 here. Sometimes the coefficients and powers are related, but sometimes not. We have a lot more to say about that. We would say that this reaction, because A is a 2, we would say it's second order in A. Because B has a power of 1, we would say it's first order in B. And because you sum these together to get a 3, we would say it's third order overall. Okie dokie. Now what? So we will be doing experimental determination of rate laws in our next lab. So let's talk about how that works. If we write a rate law for this guy, an experimental rate law, including variables so far, rate laws have the formula, have the setup of rate equals K, rate constant, times reactant concentration raised to some power times reactant concentration raised to some power. So that's a to the x times b to the y. C and D do not appear in my rate law. X and y must be determined by experiment. And you have to run several experiments in order to determine x and y. Let's explain why. If we run through the example and try to determine x first, let's compare experiment 1 and 2 looks like a good thing to compare, and I will explain why. What we're going to do is we're going to put experiment 1, no, let's put experiment 2 on top. You'll see why in a second. Experiment 2 divided by experiment 1, rate law of experiment 2 divided by rate law of experiment 1. Well, let's do that. The rate of the reaction, experiment 2, is 0.44 molarity per second. The rate law the rate of experiment 1 is 0.11 molarity per second. Rate constant experiment 2 divided by rate constant experiment 1. We don't know anything about rate constant yet. Molarity of experiment 1A, that's 0.717 divided by 0.17, experiment 2. My words and my handwriting are not going together, but maybe you're following along. Experiment 2 divided by experiment 1, 0.17 raised to the x, 0.17 raised to the x. And then B is 0.44 raised to the y, divided by 0.22 raised to the y. Whew. Okay, what can we do to simplify this? Well, rate constants are the same as long as temperature is the same. If all of these reactions were run at room temperature, or all of these reactions were run at 300 Kelvin, all of these reactions, it doesn't matter what temperature they were run at. The rate constant is the same if the reaction is run at the same temperature. So K1 versus K2, that gets to cancel out because some number over the same number is going to equal 1. Some number over the same number raised to the same power is going to equal 1. So we chose to compare experiment 1 and 2 because experiment 1 and 2 had the concentration of A held constant, but the concentration of B changed, so we can isolate our B variable and compare the reaction where it is changing, but A gets to cancel out. So our simplified setup is 0.44 divided by 0.11 equals 0.44 divided by 0.22. And as you may recall, 0.44 raised to the y divided by 0.22 raised to the y is the same thing as 0.44 divided by 0.22 raised to the y, right? Right. So we can simplify inside our parentheses and get 4 equals 2 to the y. Well, the cool news about this is we can solve it without doing what I'm about to tell you, but we can already know that 2 squared equals 4, so y equals 2. But if you didn't have easy numbers like this, how do you solve for y? You take the log of both sides, or the natural log, it doesn't matter. Log of 4 equals log of 2 to the y. The reason you would do that is logarithm rules say you can pull exponents out front. So log of 4 equals y times log of 2. That becomes y equals log of 4 divided by log of 2, and you plug that in your calculator and you get y equals 2. Hurrah! So, backwards, y equals 2. This reaction is second order in B. I'm going to flip forward. Rate equals K times A to the X power times B squared. That's what we know so far. How do we determine X? Well, we chose to compare 1 and 2 because A stayed the same and B changed. Our life is easier if we now choose to compare 2 experiments where B stays the same but A changes. So I can compare experiment 1 and 4 because A changes and B doesn't. I can compare experiments 1 and 5, 2 and 5, nope, not 2 and 5, 4 and 5. It doesn't really matter. Or if I even did fewer experiments, now that I know the coefficients of B, I can solve it even when B changes. I can solve for X even when B changes. But I feel like the math is shorter and faster if I compare when B stays the same. So let's compare experiments 4 and 5 just because. 0.51, 0.34, 51, 0.34, that's what I just said for X's concentration, A's concentration. So apparently that means I'm putting 5, K5 over K4, rate 5 over rate 4, rate 5 over rate 4, 0.33, 0.22, and this one is 0.22, 0.22 raised to the 2. We get to cancel all that out. Forget this, and we simplify. 0.33 divided by 0.22 is 1.5 equals 1.5 raised to the X. Oh, cool. X equals 1. Anything raised to the first power is itself, right? If we wanted to do the logarithm to fix it, sure. Our final experimentally determined rate law is rate equals K times A to the first power, B to the second power. Do you have to include the 1 on A? No, but I'm doing it explicitly now. If we needed to determine the value of the rate constant, you can determine the value of the rate constant now because you know A's concentration for one of your experiments and B's concentration for one of your experiments and the rate for one of your experiments. So you could pick experiment 3 and plug in rate A and B and solve for K. And as long as you're at the same temperature, K stays the same. We're not going to solve for K right now, but I'm saying that we could. That was so fun. How about some more? And this time we've got 3 experiments. Let's be a little more choosy in how we start. 3 experiments, 2 reactants. Our rate law would be rate equals K times CH3I raised to the X times hydroxide raised to the Y. Okay. How do you determine X and Y? Well, you need at least 2 experiments where one of your reactant concentration stays the same. So in inspecting our experiment conditions, our CH3I was never the same. I need to choose to compare, to isolate one of my variables to solve for it, then I can move on. So I'm going to compare experiment 2 and 1 and 2, so that I isolate and can solve for X first. Well, let's put 2 over 1 just because it'll give us fraction numbers that make our solving necessary to use the log, because I think that I would like to see you use the log. 2 over 1, that's rate over rate, molarity per second, micromolar per second actually. K over K, it doesn't really matter, but we'll write it there so that we're formal and official. 0.1 over 0.1, we'll write it there so that we're formal and official, but it doesn't matter. 0.85 over 1.4 raised to the X. So we simplify. 5.53 divided by 15 is 0.369 equals, forget K, forget 0.1 over 0.1, 0.607 raised to the X. These numbers look much more experimentally accurate than the past numbers. When we do our lab, it's probably going to look more like these numbers that don't come out wholesome. Where do we solve from here? Take the log of both sides, log of 0.369 equals X times the log. Maybe that was too big of a jump and you don't want me to do that, but the reason I do the log is so that I can pull the X out front. So log of 0.369 divided by log of, 607. 607 equals X. X equals 1.997. X equals 2, because we really need it to be a whole number coefficient, a whole number exponent. X equals 2. So that makes my rate law. Rate equals K times CH3I squared times hydroxide to the Y. We need to now determine Y. It doesn't matter what I choose here, except I don't need to compare experiments 1 and 2 because I need the hydroxide concentration to change. So if I compare 1 and 3 or 2 and 3, it doesn't matter. Let's compare 1 and 3 just because I made a choice. Let's do it. 1 and 3. We'll put 1 on top of 3. Whoops. That means 15 divided by 15.31 equals K1 over K3, but it doesn't matter. We just determined that X had a value of 2. We said we're doing 1 over 3. 1 over 3. 1.4 over 1.00 and 1 over 3.1 over 0.2 raised to the Y. This time, we cannot cancel out this thing, but we have all the information we need to solve it. So, simplify. I got 0.979, sure, equals 1.4 divided by 1 squared is 1.96 times 0.5 raised to the Y. I'm just simplifying. So then I divide by 1.96 and get 0.5 raised to the Y equals 0.499, so 0.5. I can log both sides and do that kind of thing, or I can say, oh, Y equals 1. Yeah, that's nice. So our final rate law for this one is rate equals K times CH3I raised to the second power times hydroxide raised to the first power. It's a third order overall reaction, second order in methyl iodide, first order in hydroxide. If I needed to, I could go and solve for K by choosing any of my 3 experiments and plugging in the data and getting K, because as long as I'm at the same temperature, the K is the same. That's rate laws.